A capacitor is a passive two-terminal electronic component that stores electrical energy in the form of an electric field. It consists of two conductive plates separated by a dielectric material. The most common use for capacitors is energy storage, power conditioning, electronic noise filtering, remote sensing and signal coupling decoupling. Due to the fact that capacitors are an important and versatile function to varied applications, they are used in a wide range of industries. When a voltage is applied across a capacitor, an electric field is created between the two plates. The plates become charged with opposite polarity, and energy is stored in the electric field. When the voltage is removed, the capacitor discharges, releasing the stored energy. The ability of a capacitor to store energy is measured by its capacitance, which is the ratio of the electric charge stored in the capacitor to the voltage across the plates. The capacitance formula is C equals Q by V, where C is capacitance in farads, Q is the charge in coulombs, and V is the voltage in volts. If Q is the charge on one plate, then the surface charge density is sigma equals Q A sigma equals charge by area of the plate, equation 1. By Gauss's law, the electric field intensity between the plate of parallel plate capacitor is E equals sigma by epsilon naught. The electric field intensity is electric field intensity equals voltage by distance voltage equals electric field intensity multiply by separation of the plates. Voltage equals sigma by epsilon naught d, from EQ1. V equals QD by epsilon, naught is Q equals CV. C equals Q by V. C equals Q by QD by epsilon naught, C equals a epsilon naught by D. If an insulator of relative permittivity epsilon R is inserted, then C equals a epsilon naught. Epsilon R, by D. This is the equation for capacitance of parallel plate capacitor. The capacitance of a capacitor depends on several factors, including the area of the plates and the distance between them. In this experiment, we will demonstrate how capacitance varies with plate area and separation. We will use a voltage source with a range from 0 to 1.5 volts and a capacitor with varying plate areas from 100 mm² to 400 mm² and separation distances from 2 mm to 10 mm. As we charge the first capacitor, we can see that the capacitance increases directly as the plate area increases, while the separation distance remains constant. Now, as we increase the separation distance while keeping the plate area constant, we can see that the capacitance decreases. Finally, we will vary both the plate area and the separation distance and observe how the capacitance changes. As we can see from the graph, capacitance is directly proportional to the plate area and inversely proportional to the separation distance. Capacitors are essential components in electronic circuits, and understanding how they work is crucial for anyone interested in electronics. We hope this video has helped you understand the concept of capacitance better. Thank you for watching.